Okay, so this is our question for the OC, for the open circuit test and the closed circuit test of a transformer. So the question reads, the open circuit and short circuit test on the 8 kVA 220 slash 110 voltage transformer yielded the following results. So these are the results. You have the open circuit test result. We have the power of the open circuit test given as 116 watts. Current of the open circuit to be 1.65 amps, and the voltage of the open circuit we have 210 volts. So this one is on primary to secondary. This one is being opened here. Then now the short circuit test, these are the readings. We have power of the short circuit, we have 172 watts. Power in the, current in the secondary, in the short circuit, we have 28 amps, and voltage of the short circuit we have 12 volts. So this one is on primary to secondary, it has been short circuited. Okay, so the first question, state the value of the core losses. State the value of the core losses, 1 mark. So now, when dealing with, I'll start with the short circuit here. When dealing with the short circuit test, this one you determine the copper losses. This one you determine the copper losses. You determine the copper losses. This one you focus on the copper losses that occurs, and the equivalent resistance has to be there, the impedance and the leakage reactance, all those you have to calculate them. So you find that now the core losses, you won't find them when you are performing the short circuit test. The core losses, which are the iron losses. So the core losses here, which are the iron losses, the core losses, you won't find them when you are performing the short circuit test. The main reason is because they are very much small, whereby you cannot even notice them. The core losses, which are the iron losses, when you are performing the short circuit test. So the short circuit test, you want to concentrate on the copper loss, and you're going to have the equivalent resistance, the equivalent impedance, and the leakage reactances. Those are what you're going to find. But when it comes to the open circuit test, when you're dealing with the open circuit test, this one here now, you determine the no load current. You're going to determine the no load current and the losses, which are the iron losses. So those losses are going to determine under the open circuit tests are the iron losses, which are the core losses. The copper losses on the open circuit test, they're negligible, whereby they don't, affect anything. They're very much small. They are there, but they're very much small, whereby you just try bombs like to ignore them. Okay, so now here the question says state the value of the core losses. So now, like what we've said, that the core losses, these ones here, they have to be performed where the core losses, which are the iron losses, they have to be performed where on the open circuit test. So now, since the core losses has to be performed on the open circuit test, what loss have we been given here? So this is the loss here that we've been given, the 116 watts. So you find that this here, the 116 watt, this is the power. So the power of the core is equals to the power of the open circuit test, which is equals to what? 116 watts. So 116 watts. So this is your answer for the first question, which is the core losses. Then when it comes to the copper loss we were dealing with what? The short circuit test here. So the short circuit test, this one, it is the one that you're going to concentrate with the copper losses, the short circuit test. And on the copper losses here, we've been given the short circuit test as in, we've been given the current here on the short circuit test. We have the current being given as in 28 amps. Then the short wattmeter readings, the short wattmeter readings, which is as the power have been given as in 172. So 172. The short circuit power we've been given 172 watts. Okay, so now how can you calculate the how can you find the primary rated, because we have to know the primary rated for this one here, the primary rated of the transformer. So now how can you calculate the primary rated of the transformer? The copper losses here, we have to know the copper losses here, we have to know the loss of the copper at full load. You can at full load and at 28 amps. So we have to calculate the copper losses at full load and at this current here, because we don't know the full load of this transformer. So let's try to calculate the current of the full load of this transformer. Then when you calculate the current of the full load of this transformer, we'll be able to tell the copper losses at that full load. So here the only load, the only loss that we've been given is that loss of 28 amps, which is 172 watts. So at 28 amps, we have 122 watts as in the copper loss. Now, what about at full load? Let's try to calculate that. So on the transformer, this 8 kVA, this is the rated power that we're going to find on the transformer. So this is the rate that you're going to find there on the nameplate of the transformer. So to say that this transformer has been rated as an 8 kVA. So this is what you are going to find on the nameplate of the transformer. Okay, so since we have the ratings of the transformer as in 8 kVA, so this is the rating of the transformer as in the 8 kVA. So what are we going to do with it? We can use this one to calculate the primary rated current. So that primary rated current we are going to calculate, it will be the one which is going to determine the full load. The full load current. We're going to have the full load current and the full copper losses. The full copper loss power. Yes. Okay. So from there, we're going to have the primary current here. From the Ohm's law, we know that V is equals to IR. This is the Ohm's law. Now we are dealing with the current here together with the power. So we have power is equals to IV. This is the formula for power. Power is equals to IV. Now the current, we have the current, the power at full load is the one that we have to calculate, and this is the voltage that we've been given on the primary side. This is the voltage that we've been given on the primary side. Remember that what we want to calculate here, it is what we want to calculate here, it is the power of the full load of this transformer. Okay, so we have the rated current here. We're going to have the rated current which is equals to the ratings of the transformer, which is 800, which is 8 kVA. So we're going to have the rate of the transformer here, which is the supply 8 kVA. Then we're going to divide everything by the voltage on the primary side. So this is the formula that you have to use. So now we have the rated current here. The rated current, which is equals to this one here. This is the supply. This is the ratings of the transformer being given that it is 8 kVA. 8 kVA, that's 8,000 volt amps. So I'm going to have 8,000 here. You divide everything by the voltage on the primary here. The voltage on the primary, we've been given that it is 210. That's the voltage on the primary. So we use 200 and 210 200 and no, that's 220. So this is 210. We have 220. This is the voltage on the primary rated. This is the rated voltage, 220. So we're going to have a 220 here. So when you divide this now, what is 8,000 divided by, what is 8,000 divided by 220? We're going to have on the calculator. So 8,000 you divided by 220, you have 36. We're going to have 36.3636 amps. So this is the rated current of the primary on the primary side. This is the rated current on the primary side, as in the full rated current on the primary side. We have 36.3636 amps. So from there now we can calculate the power, the copper losses. So we're going to have power of the copper loss at full load. Don't forget about this. At full load has to be equal to the power of the short circuit. You multiply everything by the current of the rated. You divide now by current under the short circuit. So this is how we calculate now the losses, the full losses there which is happening in the transformer. So power on the copper side, the copper loss at full is equals to this one here, the power on the primary. This one here is the short circuit power that has been given on the secondary part here. This is the short circuit that has been given on the secondary part to be 172. So you have 172 here. So you have your 172, you multiply everything by the rated current, which is 36.3636. You divide everything over the current, the rated current there. It is you've been given that it is 28. This one here, 28 on the short circuit side. So you divide by 28. So if you do your calculations here, what is 36.36? You divide it by 28. First we start by divided by 28. You're going to have 1.297. So it will be 172. You multiply by 1.29 871. Okay. So if you multiply this now by 172, if you multiply now that by 172, if you multiply that one now by 170, so we've made a mistake with the formula. So the formula here, this one, it was supposed to be squared. Yeah, so it's supposed to be squared. This is the main formula. It has to be squared here. So since we have this, we have the power. We have power on the copper side, which is at full load, is equals to the power of the short circuit in brackets we have the current which has been rated for the full transformer over current on the short circuit side. Then you square it. Okay. So now for this answer that we found here, this answer here, we just have to square it here. So we just have to square it. So this one, the 1.2987, if you square it, you're going to have something like I'll take this one here. Let me just try to erase this part. Okay, so now if you multiply that, you're going to have 1. So we have our 172 here. It still stands. Multiply by, remember, still solving what is inside here. 1.68 1.6866. Then you multiply that now by 172. So we're going to have a 290. So we're going to have a 290.09, which is 290.1 watts. So this is the loss, the copper loss. This is the copper loss at full load. So this is the copper loss at full load. So we have the copper loss at full load is equals to 290.1 watts. Then we have now the copper loss, not at full load, but the copper loss of the short circuit. The copper loss we have 170 watts. So this is what we've been given here. So these are our answers. You have these two. Okay, so this is the losses of the copper. This is the copper loss at full load 290.1 watts, and this is the losses, the copper losses at the short circuit being given as 172 watts. Okay, so we proceed to the next question. So the next question says calculate the equivalent primary phase angle. Calculate the equivalent primary phase angle. So that equivalent primary phase angle we have to calculate. Let me just try to erase this part. Okay, so calculate it from here. So our answers, the first answer, let me just try to write our answers here so that when it comes in terms of substituting, we are able to substitute without having any difficulties. Okay, so the first answer here, the core loss, okay, so we just do this. Okay, so we just write A1, the core loss here. The first answer for the core loss, we have PS, the open circuit, power of the open circuit test. We've been given that it is 116 watts. Then the copper losses, we had two answers, the one at full load and the one which is at the, what's this, at the 28 amps. So the one at full load, we have power, the loss, the power, the copper loss power at full load, we calculated as in 290.1, which is here, 290.1 watts. Then the copper loss at 28 amps, we've been given that it's 172 watts. Okay, so these are our answers. So we move to the next question B. So question B, it says that calculate the equivalent primary phase angle. You calculate the equivalent primary phase angle. So how do you calculate this equivalent primary phase angle? Let me try to erase this part because this is where we're going to be writing our answers from. Okay, so our calculations will be done. Our calculations will be done here. Okay, so question B1, equivalent primary phase angle. So the equivalent primary phase angle, it can also be called the angle of the equivalent series in impedance. So this has to be done from the short circuit test side. This is where the testings has to be done. So for us to calculate the equivalent primary phase angle, we have to do the testings here. This is where our answer has to come from. Okay, so now the impedance of that equivalent has to be equal to the equivalent of that, the impedance of that equivalent has to be equal to the voltage of the open circuit, the voltage of the, because the testings are being done on the secondary side, the voltage of the short circuit, we divide it by the current of that short circuit. So this is the impedance, so which is equal to the voltage of the short circuit, the voltage here of the short circuit we've been given as in 12 volts divided by the current we've been given that it is 28. So if you divide what is 12, you divide it by 28, you're going to have 0.428. Going to have 0.428 57. Okay, 57. So this is the impedance. So what do we do? 57 amps. Okay, I mean 57 ohm. I mean 0.42857 ohms. It's been ohms. It has been measured in ohms, the impedance. So now from the impedance, we have to calculate now the equivalent resistance. So the equivalent resistance, we're going to calculate it together with the what's this, power of the power on the short circuit, because all the readings have been done on the short circuit side. You divide it by the current on the short circuit side. Remember, it's squared. Remember, we calculate power. Power is equals to I squared R. This is the formula for power. So this is what is here. Then you just make R the subject of the formula. So how do you make R? You divide both sides by I squared, also here by I squared. Then you cancel, meaning you're going to have R is equals to power over current. So now, since the readings have been done on the short circuit side here, the short circuit, this is where the readings are being done. Okay, so we short circuited everything, and we want to calculate now the equivalent resistance which is taking place there. So this is what we are going to do. It's just a matter of substituting and be able to calculate and find the equivalent resistance. Okay, so let's calculate. So when you substitute this, the power of the power on the short circuit side, we have 172 over current on the short circuit, we have 28. Then you square it. So you have 172. You divide it by what is 28 squared? 28, you square it, you're going to have 748, 784, sorry. Yeah, so if you divide now this one, 784, you divide it, 784, I mean 172, you divide it by 784. So you're going to have 0.2193 193. Let me say, I'll just round it off. 193 9 0.21939. Okay, I'll have something like this. So this is also, it's been measured in ohms. Remember, we have the ohms here. Okay, so we have this. So this is the resistance. So now from the resistance, then we have to calculate now the reactance. The reactance for this here, this is the formula that you have to use. Okay, the equivalent reactance equals to, so we have this here, you subtract squared, you subtract the resistance, the equivalent resistance there squared. Okay, so this is the formula that you are going to use. So we have the reactance here, which is equals to this one here, the impedance we calculated to be the impedance we calculated to be 0.42. So we have the root of 0.4857 squared minus 0.21939 squared. Okay, so this, if you punch on the calculator, find that the equivalent reactance has to be equal to 0.42857, you square it, minus 0.21939 squared. Okay, so we're going to have the square root of 0.13554. So now, if you find the square root of this, now your answer has to be equal to 0.3682. Okay, 0.3682 okay, ohms. So these are the values that we have. Now, since we know these values, now how do you calculate now equivalent impedance angle, this one here. So now, since we know these values now, how do you calculate the equivalent primary phase angle, which is the equivalent impedance angle? So this is how we can calculate this. So after calculating, let me just erase this part here. So now after calculating the reactance, resistance, and the impedance, we are going to have to calculate this angle. So this angle here that we're supposed to calculate has to be equal to the tan, the inverse of that tan, okay? So which is equal to what's this? The reactance, the equivalent reactance over the equivalent the equivalent reactance over the equivalent we have the equivalent, this is the equivalent reactance, then everything now we divide it by what's this, the equivalent resistance, the equivalent resistance. So this is the formula. So you have this. So now from here you can substitute. So the equivalent reactance will have 0.36368 you divide it by the equivalent resistance we calculated to be 0.2193, 0.2 0.2193, 0.2193. So if you punch this on the calculator, 939. So if you punch this on the calculator, remember there's a tan here, the inverse of this tan. So when you punch this on the calculator, you have your 0.3, you have 0. Okay, so 0.3682, you divide it by 0.21939. You're going to have those values 1.678289804. Then you press shift, then turn on your calculator. So the answer that you're going to find for the angle, this equivalent angle here, is equals to 59.2 degrees. So this is the angle, the equivalent angle on the primary side. So this is the equivalent primary phase angle. So this is what we have here. Okay, so from there, A1, then B1. B1 we calculated it to be on the primary angle 59.2 degrees. Okay, so let's go to question 2. Question 2, it says the no load phase angle. No load phase angle. So now how do you calculate the no load phase angle? Let's try to erase this part. So this is where the our calculations are going to be done from here. But we need to keep this. Okay, so these answers, the impedance, the reactance, we will need them. So what I'll do is, let me just try to copy this and okay, so let me try to copy this. Okay, we cut, take them down here because we need them. Okay, we still need these calculations. We still need these calculations here. We still need these calculations. So this is the the 0.42, it was the impedance. This one, it's the impedance. Okay, then we have to take the resistor. Okay, take the resistor. So this is the answer that we want. So this is the resistor, the equivalent resistance. Then you have the reactance, the answer for the reactance. This is our answer for the reactance. Okay, so we'll also take this because these values we still need them. Okay, down here. So this is for the reactance. Okay, so this is the equivalent. Okay, so we have this now. Let's try to solve for the no load phase angle. Let me just try to erase this. Okay, so now yeah, we start. So the no load phase angle that we have to calculate, the no load phase angle that we have to calculate, it's nothing but that angle from the open circuit test, the angle from the open circuit test, which is dealing with the power factor. So now for us to calculate the no load phase angle, we have to know the power factor on the open circuit test side that we're dealing with. Okay, so now how do you calculate this one here? So we have, this is the formula that we're going to use. The power on the open circuit part is equals to the current on the open circuit part multiplied by the voltage on the open circuit, then everything multiplied by the no load phase angle. So now from here we can make the no load phase angle the subject of the formula by doing what? By dividing by current on the open circuit side multiplied by voltage on the open circuit side, everything by the same. So to be current divided by this. Okay, so since we have this, meaning this and this will go. Sorry. Okay, so meaning this and this will disappear, will remain with the cos here. So to be the cos theta equals to power on the open circuit over current over current on the open circuit multiplied by the voltage of the open circuit. So we have this. Okay, so this is our main formula we are going to use. So we're going to use this formula here. This is the formula that we have to use. Okay, so let me just take it here. So this is the formula that we're supposed to use. Okay, so since now we have this, it will be easy for us to calculate the no load phase, the no load phase angle. So now the power on the open circuit have been given to be 116 watts. The current on the open circuit have been given to be 1.56 amps. Then the voltage have been given to be now here we have this was the, we have 210. This was the error. It was supposed to be 220, not 210. So they just made a mistake here. So it was supposed to be 200. I mean 220. This is the what's this? This is the voltage on the primary side for that of the transformer. But this one now, after carrying the test, this is the voltage that they had to come up with. So we are going to use the same cos theta equals to the power on the open circuit side, we have 116. You divide it by the current on the open circuit, we have 1.5, 1.65 multiplied by the voltage on the open circuit here. Open circuit voltage has been given to be 210. Remember that these readings here, these readings here, you can only find them on the transformer's nameplate here. But these are the tests now after carrying out the test. These are the readings that appeared after carrying out the test. So under this voltage on the open circuit, the voltage on the open circuit, it was 210. So it will be now the cos theta, which is the no load cos theta equals to 116. You divide it by, you have 1.65. If you multiply what is 1.65, you multiply it by 210. you're going to have 346.5. 346.5. So we have 346.5, this one here. If you divide what is 116 divided by 346.5, you are going to have divide this by 116. So we are going to have 0.335. Okay, so 0.335 0.335 is the answer that we have after dividing this. So now remember it is the cos of theta, so meaning our no load angle here, our no load angle has to be, so that when you press shift in the cos, we have 70.44 degrees. So this one becomes our angle. So this is our answer for question the no load phase angle, question 2b. Okay, so question 2b, we have this one here, 70.44. So we get the same here as an answer. Let's press it here. So this is our answer for B2. For B2. Okay, so this is our answer for B2. Then we go to question B3, the working current component. The working current component. Let me just try to erase this. Okay. Okay, so now the working current component, this is what we have to calculate. So the working current component, this one, these are the core losses. These are the core losses. So these are the core losses. The current component, the working current component we're going to find deals with the core losses, which are an active component. So now this one can be calculated as in the working current equals to the working current equals to the current of the open circuit multiplied by the cos theta. Then we calculate, that's it. So here when you substitute the current of the open circuit, you've been given to be 1.65 multiplied by the cos of what's this, the cos of the no load phase angle. This is the cos that would be we're talking about. It is the no load phase angle. So the cos of this one was cos 70.44. So now if you multiply this, the working current equals to, if you multiply what is 1.65 multiplied by cos 70.44, we are going to have 0.552. So we're going to have 0.552. So the 0.5524, this is the working current. So this is the working current component. So this is the answer for question B3. Then the magnetizing current. How do we calculate the magnetizing current for number 4? So the magnetizing current is equals to the same open circuit current you multiply by, now here it is the sine of the angle, so sine theta. So now since we have this one here, so the magnetizing current here, these are the reactive component of the open circuit current, Okay, so now the magnetizing current here, we have this is what we are going to have. So it will be the magnetizing current equals to, what is the open circuit current? The open circuit current will be given to be 1.65. Then we multiply everything by sine. Remember that our angle we calculated our angle to be 70.44. That no load phase angle 70.44. So the magnetizing the magnetizing current is equals to, if you multiply what is 1.65, you multiply by 70.44, we are going to have 1.65, oh sorry, the sign, 1.65 you multiply by sign 70.44, we are going to have 1.55. We're going to have 1.5 1.55 1.555 amps. Okay, so if you want, you can round it off to be 1.56 if you want. So we have something like this, but I just want to leave it maybe to 3-4 decimal places. So this was magnetizing the magnetizing current component. So we have this. So this one we name it as in, now the space here is for, okay, let me just try to erase this part. Indeed, let me erase this part here and put our answer. Okay, so the working current so the magnetizing current and the working current. So I'll get the two. These are the important answers we want. Okay, so we have question. Let me just try to, okay, let me just try to put them here. So we have question. So this one is question b what, b3. So we have 3 and 4. Okay, so b3 and 4. We go to the next question. So the next question says, question 5, the transformer efficiency on full load at a power factor of 0.76 lagging. So it was lagging, not leading. Okay, so since we had that, so this one was lagging. So now for us to calculate the power factor, I mean to calculate the transformer efficiency, on the full load at power factor of 0.76, which is lagging, we have to consider the power output. We have to consider the power output of the transformer. So the power output of the transformer, is to be equal to the transformer ratings. Here I'll represent as in S, the transformer ratings, which is S, then I'll multiply everything with the power factor. Okay, so now which is equal to, so the transformer rating, it is 8 kVA, which is 8,000. Then I multiply everything by the power factor, which is lagging, as in 0.76. So I multiply everything by 0.76, it's lagging. So now, so what is 8,000? You multiply by 0.76. We're going to have 6,080 watts. 6,080 watts. So this is the power output of the transformer. So since we have this power output of the transformer, what is the next parameter that we have to calculate? Let's look at the losses. So the total losses of full load, the total losses of the full load has to be, let me say, the total losses of the full load has to be equals to, here we're going to have the core losses, we add plus the full load losses, the one we calculated at first. Yeah, this one, the copper losses at full load, which is 290.1 watts. So plus the copper losses at full load. Okay, at full load. So this is the formula that we have to use for us to calculate the efficiency of the transformer. Remember, everything we multiply by what? If you want to find the percentages, we multiply by 100, because the percentages add up to 100. So the efficiency now of this, has to be here the loss, the total losses at full load. The total losses, first we have to calculate the total losses. That's when we come to efficiency now. So let's calculate the total losses. So we have the core loss here, the core loss here, which is the iron losses, we've been given to be 116. Remember, the iron losses has to be calculated on the open circuit side. So which is given, which were given to be 116 watts plus the what's this, the copper losses at full load calculated to be 290.1 watts. So we had 290.1 watts. So if you add this here, what is it? 116 plus 290.1. So we're going to have 406.1 watts. So this one equals to 406.1 watts. Okay, so this here is the total loss. Now we can calculate the efficiency of a transformer at full load. So this is the total loss here at full load. We have to know it as well. So we have 406.1 watts. Then how do you calculate now the efficiency? Since now you know the losses, how do you calculate the efficiency? So the efficiency is equals to the output power over the output power plus the loss that we've calculated to be 406.1. So if you want, you can multiply everything by 100, it's still okay. Okay, so now the efficiency, which is equals to the output power here, we calculated it to be here, the output power we calculated to be 6080 watts. 6080 watts, you divide it by the output power, which is 6080 watts, you add plus the loss, which is 406.1. So now if you do this, what is 6080? So we have 6080, you divide it by what is 6080? 6080 plus 406.1, we're going to have 6,400. We're going to have 6,486.1. So now if you divide this now, if you divide this by, if you divide 6080 divided by 6,486.1, 6,481, you are going to have 0. You're going to have 0.937. 0.9374. So 0.9374 that we have, this one here is our magnet, what's this, our efficiency. So if you want, you try, but let's just try to bring this down here. If you want, you can leave this, you can leave it as a percentage. So how do you leave it as a percentage? You multiply just by what, okay, somewhere here, so that's here down. Okay, so you can multiply everything by what, by 100. So if I multiply this by 100, so the point, if I multiply this by 100, I multiply by 100, so I'm going to have a 93.7. So because the point is here, it moves 1, 2, and this 0 disappears. So I'm going to have a 93. So the efficiency of the transformer at full load, the efficiency of the transformer on full load at power factor of 0.76 lagging, I'm going to have 93.74%. Okay, so this is the efficiency. Let me just write the formula of the efficiency nicely. Okay, so this is So this is the efficiency of the transformer on full load at a power factor of 0.76 lagging. Okay, so now since we've calculated the efficiency, how do you calculate now the percentage voltage regulation? Voltage has been regulated, has been dropped. So we are dealing with the voltage drop and the secondary voltage. So let's now look at the voltage drop, voltage regulation. Try by all means like to regulate or reduce. So this is electrical machine. You know, once you just know how to calculate, the part becomes simple if you just love the calculations. So the electrical machines becomes easy. So let me just erase this. So the last part is we have to talk about the percentage, the voltage, the percentage voltage regulation and the secondary voltage. So how do you calculate that? So this is question now 6. Okay, so now how do you calculate the voltage regulation? This is question 6. Okay, so now the percentage voltage regulation and the secondary voltage uh, voltage, we can use the voltage drop on the primary due to the series impedance. If you draw the circuit, you're going to have some, once the calculations are being done, you're going to have something like you have the resistance here. Okay, so this will be your equivalent circuit, like, because the resistance, we've calculated the resistance and we've calculated the impedances and the reactance. So we're going to have something like this. Now they want the voltage drop at this point here, the voltage drop at this point here. So how do you calculate this voltage drop? So the way we can calculate this voltage drop here is by considering the series impedances. Okay, so for us to calculate, to consider the series impedance, we have to know the load angle. So the load angle that we have to know, we've been given that here the transformer was lagging, not leading. So it was lagging, it was lagging with the power factor of 0.76. So the power factor that it was lagging, it was 0.76. So we use the same course to calculate the angles being involved. So 0.76. So if you place this on the calculator, shift, you have your cos of 0.76. So you're going to have the angle of 40, 40.54. So this is your angle when this is your angle when the transformer it was busy. This is the angle when the transformer it was lagging with 0.76. So the angle that has to come out, it was 40.54 degrees. So now since you've calculated the angle, the voltage drop on the primary side, the voltage drop on the primary side has to be known as well. So the voltage drop on the primary side, this one will represent the primary and the twos will be representing the secondary part. So the voltage drop on the primary side, this is the primary, this is the primary, this is the secondary. So the voltage drop on the primary side is equals to the rated current, is equals to the rated current, so it will be the equivalent resistors, you multiply by the cos of that angle given, plus. The main reason why I'm putting a plus here is because it's lagging. If it was leading, there was supposed to be a negative here. Okay, then you multiply by the reactance, equivalent reactance, with the sign of the angle load given. So this is how we can calculate the voltage drop on the primary side. The question here, it says percentage voltage regulation and the secondary voltage. So the percentage voltage regulation, we have to know the voltage drop on the primary side. So this is the calculation under the voltage drop on the primary side. Okay, so we are going to have the voltage drop on the primary side equals to the rated current. The rated current we calculated it to be, what was our rated current? Uh, okay, so since now we've forgotten about the rated current, it was the rated current, it was the 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 the, the supply transformer. This is the ratings on the ratings of the transformer, which is in kVA. We represent it as in S. You divide it by the current on the primary. I mean the voltage on the primary side. So the rated transformer, it was 8,000 and 8,000. You divide it by the voltage on the primary side, it was 220. So if you punch this on the calculator, it is 3. This is the main reason why I've been writing answers, so that when it comes in terms of substituting, just pick them and substitute without going back again. So 36.6, 36.3636, yeah, amps. So this was the rated current of the transformer. So let's just try to write it somewhere. To just put it somewhere. Okay, so the rated current. So this is the rated current. Okay, so this is the rated current, 36.3636. Okay, so now since we know the rated current as in 36.3636 amps, here we have 36.3636 amps. Okay, the equivalent resistor here we had 0.2193, 0.2193, 0.21939. Then you multiply by this one here. There is a multiplication. You multiply by the cos of 40, cos 40.54, because that's the angle that you've been given, plus here the equivalent reactance 0.3682, 0.3682, we multiply by the sine of 40.54. Okay, so now if we perform the calculations nicely, so the voltage drop on the primary side, if we perform the calculations nicely, so let's try to go step by step. We have 36.3636 in bracket. What is 0.2193? 0.2193 multiplied by cos 40.54. We are going to have 0.1667 plus, we do the same. What is 0.3682? You multiply by the sine of 40.54. You multiply by sine 40.54. We have 0.2393. Okay, so from there we have the voltage drop on the primary side. We have 36.3636. So this one, if you add this plus, if you add plus 0.1667, we have 0.0406. Okay, so now this one, if you multiply now by 36.3636, which is the rated current, you are going to have a 14. So the voltage drop on the primary side, you're going to have a 14.76 volts. So this is going to be the voltage drop on the primary side. So now, since we know the voltage drop on the primary side, let me just try to bring it down as well. Yeah, might need to use it. Okay, so that's the voltage drop on the primary side. Then, since now we've calculated the voltage drop on the primary side to be 14.76 volts, now the percentage regulation, it can be easily calculated. Since now we know the voltage drop on the primary side, we can calculate now that percentage, the percentage voltage regulation, and easy to calculate the voltage on the secondary side. Okay, so the percentage of the voltage regulation here, which is the rated, which is relative to the primary rated voltage of 220. It is this one, the percentage voltage regulation. It is relative to the primary rated voltage as in 220. This one here. So the percentage regulation here, the percentage voltage regulation here um, has to be equal to the voltage drop of the primary side. You divide it by the voltage of the primary side, the rated voltage of the primary side. So now this one here, since it is the percentage, multiply by what? By 100. So now the voltage percentage, the percentage voltage regulation is equals to the voltage drop of the primary side of being given, we calculated to be 14. This one here, 14.76. So we've calculated to be 14.76. So we are going to have 14.76. You divide it by the voltage on the primary side here. This is the voltage on the primary side, 220. 220 multiplied by 100. Okay, so the percentage voltage regulation is equals to, if you perform now the calculations, that is 14.76 multiplied by 100, you're going to have 1476. Then you divide it by 220. So if you divide this answer by 220, we are going to have 6.7 equals to 6.71 percentage. So this one here, this is our voltage. This is the percentage voltage regulation of the transformer. So from there now, then the question continues and says, and the secondary voltage. So how do you calculate now the secondary voltage? So the secondary voltage, we are going to deal with the full load voltage, assuming no load secondary rated as in this one, the 110. This one, the 100, what's this? The 110, this one here. It was on the secondary part. This is the primary, this is the secondary. Remember? So now, assuming that there is no load secondary rated voltage of this, we have this one here, the no load secondary rated voltage. So the drop referred to the secondary is half the primary drop, which has a turns ratio. So now, since, let me just try to, okay, let me erase this part, and remember the percentage is 6.71. 6.71 percentage. Okay, let me just try to write it down here. Okay, the voltage, the percentage voltage regulation is equals to 6.71%. Okay, so let's try to calculate now the last part here. So the drop now here, the secondary voltage that they're talking about, the secondary voltage that they're talking about here, since there is the power factor of 0.76 lagging here, there's going to be a 10 ratio on the primary side. So the 10's ratio on the primary side, let me represent it as K. We're going to have V2 you divided by V1. So now our V2 is 110, you divide it by our V1, it is 220. So if you divide 110 to 220, you're going to have 0.5. So 0.5, this is the ratio that this is the ratio that you are going to find because of this here. The voltage on the primary side and the voltage on the secondary side gives us this ratio. So now from here, we are going to calculate the voltage drop on the secondary side. Now the secondary voltage that we're going to have, the secondary voltage I will present it as in 2. So the secondary voltage that we are going to have we have to first know the secondary voltage that you're supposed to calculate. We've calculated the voltage drop on the primary side. What about the voltage drop on the secondary side? Let's try to calculate that and see what happens. So the voltage drop on the secondary side has to be equal to the voltage drop on the primary side, then everything being multiplied by the times ratio. Okay, so now the voltage drop on the secondary side has to be equal to the voltage drop on the primary side. What was our voltage drop on the primary side? It was 14.76. 14.76 I multiply by the times ratio. So the times ratio here turns out to be 0.5. So if you perform your calculations here, what is 17? Is it 17 or 14? 14. 14.76 and 17. So okay, so it's 14.76. Okay, so it's 14. Yeah, 14.76 here happens to be our voltage drop on the primary side. So now we multiply by the power factor. I mean, we multiply by no, not the power factor, but the times ratio, which is 0.5. So what is 14.76? You multiply by the times ratio, which is 0.5. You are going to have 7.38. So 7.38 voltage. This one turns out to be the voltage drop on the secondary side. The voltage drop on the secondary side. Then now, how do you calculate the secondary voltage now? The secondary voltage. So now here they're talking about the secondary voltage. So this secondary voltage is going to be at full load. So the voltage on the secondary side, which has to be at full load, has to be equal to the voltage on the secondary side. The voltage on the secondary side, you subtract minus the voltage drop to the secondary. So the voltage drop, the voltage drop to the secondary. So here we've been given of 220. This is the voltage on, I mean, 110. 110 is the voltage on the primary on the secondary side, which is V2, and the voltage drop we've calculated to be 7.38. So the voltage on the secondary side, which here happens to be at full load, we're going to have the voltage on this secondary side. This one here we've been given to be 110. You subtract minus the voltage drop. This is the voltage drop now on the secondary part, on the secondary side, which we have calculated to be 7.38 watts. So now if you subtract, that is 110 minus 7.38, we are going to have 102.62. So it will be V2 full at full is equals to 102.62. So this is the voltage now on the secondary side, meaning we've calculated all the answers from the first to the last. Thank you.